Hey there, in this video I'm going to walk through some multi-level modeling diagnostics that you can do in R and especially the LME4 package. I've written some R syntax that you can find on Canvas, and we're going to kind of walk through that in this video. And so I'm going to use a couple additional packages. So if you don't have them installed, the robust linear mixed models package and then the club sandwich package. And both of these are used to get, this one we're going to use to get just robust estimates of our standard errors, and this one we're going to use to get like a robust, basically multi-level model. So it's kind of a little different framework. But all of these all that we're going to be talking about in this video is basically stuff you can run to kind of assess the tenability of the assumptions of your model. I added in some preliminary steps. Any good data analysis always begins with an observation of your data. It's always a good idea to run frequencies on all of your variables, ask for descriptive statistics, and to maybe check some correlations among your variables. And so that's what I did here. You really just want to make sure that the variables you're using correspond to, what you expected it to have. Do we expect there to be 1,185 individuals? Minority was a dichotomous variable. The minimum and maximum is 0, 1, so that's good. Our scores range from a 1 to 160. Were those the right numbers? What SES, you can see here, was it supposed to be basically a standardized score? With the mean of 0, a standard deviation of 1. The minimum maximum range from basically -3 to +3. So you just want to check just to make sure that the data correspond to what you want them to do. Same thing I'm doing here with these correlations. We really want to see higher correlations between your variables and the dependent variable. So we might look down this row here. And lower correlations among your independent variables. So we might just peruse through here just to kind of see what's going on. We could also check the correlations. By a better way to check for multilinearity is through variance inflation factors. And so you can't get those directly from your model, but I'll show you a couple different ways we could do that. First, I'm just going to run my model. I'm going to regress math achievement on SES, gender, minority status, whether the school was public or Catholic, average school SES, and an interaction between the two. And basically here, I'm just running a random intercept model just to keep things a little bit simpler. So you can see there's my model output. In the LEM4 package, it gives you these correlations of your fixed effects. So we can look through here is another good check of multilinearity. How intercorrelated are our independent variables? We can look through here. If we see high correlate, we're not as concerned with high correlations with the intercept. What that might suggest is that, that if it was like 0.9 or something, might suggest that variable isn't probably adding much to the model. Basically that it's a weak effect and not really adding much to the model. But here, everything seems fine here for that sort of multilinearity check. The performance package in R also has a nice multilinearity check. You could also do it by just running an LLS regression on the data and checking the variance inflation factors there. This package has a nice variance inflation factors, and we can see all the VIFs are pretty low. You're looking for variance inflation factors greater than 5, greater than 10 definitely indicates there's a problem. Some people get nervous when the variance inflation factor is greater than 2, but it's just something that you might want to consider what's going on here. If the two variables are highly correlated, they may be measuring the same concept, so we want to figure out what's going on. It's not technically a violation of any assumption in the model. It just aids in our interpretation of the model. If two variables are highly correlated, we can't really disentangle their effect. So it makes interpreting the regression coefficients more challenging in that case. Another useful diagnostic check is to compare the model-based standard errors with standard errors that are robust against some violation of the model. It should be. And what that suggests, so if the model-based standard errors and the robust standard errors are pretty similar, then, or let's say the model-based standard errors and the robust standard errors are vastly different, then what that's saying is you probably have some type of problem with either normality, linearity, or homoscedasticity. If the model-based standard errors and the robust standard errors tend to agree, then that's saying that violations of normality, linearity, homoscedasticity isn't having a large impact on the standard errors, and thus is probably doesn't have a large impact on the inferences that you're making from your model. I'll also kind of check whether the, does a variable, does female change from being statistically significant to non-statistically significant, or vice versa. If you're coming to different substantive conclusions, that's also an indication that something else might be wrong. So we can run these. This is from that club sandwich package. We're basically getting an estimate of the robust code of they're called, it's called a club sandwiches. They're also called sandwich estimates. And I'm basically then comparing my model that I ran with a model with the robust standard errors that I saved out in this covariance matrix here. And so we'd want to compare this model here. Notice the fixed effects are the exact same because we didn't change that. The standard errors differ. And we'd want to see how different are they between the models. And it doesn't look like we're coming to drastically different conclusions in each model. Standard errors are pretty comparable here. So it's probably not indicating a huge violation of the assumptions. Notice here the interaction term wasn't statistically significant. It still isn't. And it still, that's probably has our largest deviation in standard error. So, but for the most part, they're probably like 200ths, 300ths of a point off. So, not drastic differences between them. You can also change the type of standard error correction in here too. I'm just using, it has different ones for small sample size adjustments in there too. This is the one where there isn't a small sample size adjustment. There's also another package that runs a robust version of linear mixed models. This takes a little while longer to run, and the fixed effects will be different between each model. So it's not just changing the standard error, it's actually estimating the model. The estimation process is different. It's not a maximum likelihood estimation process anymore. This will take it a minute to run. Okay, so that took about 8 minutes to run on my computer. But you can see here, so now we can also compare our model estimates, both the fixed and the fixed effect, the coefficient estimates for the fixed effects and the standard errors across both of the models, and see if we come to substantively different conclusions Are the standard errors vastly different between models? This one we can actually look at, are the coefficient estimates vastly different between models, and kind of gives us kind of an overall assessment of the tenability of the assumptions of our model. Typically, if the model-based standard errors or robust standard errors differ, it's probably indicating that there is something wrong with either the normality, the heteroscedasticity, or the linearity. Maybe we left out an important predictor variable that should have been in there. Maybe a variable should have a nonlinear relationship with the outcome. So it's probably suggesting that there's some type of problem. The majority of the assumptions in multi-level modeling revolve around the residual, the error terms, right? We assume that the level 1 residual is normally distributed with a mean of 0 and a constant variance, that's sigma squared. Same thing with our level 2 residuals. We would assume that they are multivariate, normally distributed with a mean of 0 and some constant variance. That would be that tau matrix. In our case, we only have 1 since we only have a random intercept. We can save out our model residual. So I'm going to save out the level 1 residual here, and I'm going to get the standardized residual. Same thing for the level 2. I'm going to get the level 2 residual, and we get that from the random effects component, or function. I'm going to save it into a data frame, and then it also will export the standard deviation. So then I'm going to divide the unstandardized residual by the standard deviation to get a standardized level 2 residual. We can also get the predicted values from the model. This one will give us the predicted value, so the student's predicted math achievement score using both the fixed and the random effect. We can also get some predicted values that are only based on the fixed effects as well. So let me run these, and we'll see all of these objects populate here. So we can check the normality assumption. So here's a histogram for our level 1 residuals. Looks pretty normally distributed. Let me move my face out of the way. Looks pretty normally distributed to me. Same thing with the standardized level 2 residuals. Again, pretty normally distributed. Maybe some positive skew here, and some fairly large values as well too. We can get QQ plots, which sometimes are easier to assess the normality than a histogram. Basically, you want them to follow along like a 45-degree line here. And so for the most part, I think they do. They probably trail off a little bit here on the ends, but seems pretty normally distributed. Same thing with the level 2. You can see a little bit more non-normality with them. For the most part, I'm probably not too worried. The normality assumption is probably the one you have to be least worried about. Same thing here. We can check for outliers. I'm going to use just the describe function and maybe look at like the minimum and maximum. Snyder's and Botzker recommend if a standardized residual was greater than 4 or less than -4, probably indicate something that we might want to take a look at some more. Same thing with the level 2 standardized residuals. Where I'm going to check out this fella here, who has a standardized residual of almost 5. So we're not doing a very good job of predicting that person's math achievement there. So we could profile that school. In this case, it's a school, right? We might want to profile that school and see what's going on. We could check out the homoscedasticity assumption or that constant variance assumption. We can use the model plot here. And basically what we're looking for is a random scatter here, and that the scatter is even across this. So if we saw, you know, here the scatter looks pretty even. If we saw like a fanning shape, maybe like this, or you know, the points were looking maybe like this, they were wider on one end and smaller on the other, that would indicate a violation of homoscedasticity. You could also have more of like a butterfly effect, where they're wide, narrow in, and come out to, that would also indicate a violation of homoscedasticity. We can get the same plot by just plotting the predicted values from the model against our residuals. And you can see it's the same graph there too. We can, the Hotz books talks about an approximate Levene's test that we can calculate. And so basically, Hotz says we can just take the absolute value of the residual and basically run a one-way ANOVA with the absolute value of the residual with the ID variable or the grouping variable being the grouping variable in the ANOVA model. And so basically this is really just looking at, are the residuals, is the variation in the residuals the same across each level of our level 2 variable. And so that's what I'm doing now. You can see this. Oops, I probably need to do all this too. And so you can see this result is statistically significant. So it's indicating that yes, there is a violation of that homogeneity of variance. It's probably picking up some of the tails over here. You know, it's not as wide, not quite as wide. Now it's getting a little bit wider, you know. Also the F values, kind of not too large. We could also look at kind of just the groups, the mean and standard deviation of the groups, and we could see, you know, how different is the average residual across each group. We can see we get a low average residual for this group. It's, you know, almost 40% larger than this in the first group than it is in this one. But for the most part, we're getting a lot of 5s and 4s, 3s, 4s. We can look at just the variation in the residuals across each group. And, you know, just kind of perusing these really quickly, I'm not too worried about the homoscedasticity assumption. Also, our robust standard errors test didn't really suggest too much of an issue there as well. We could also graph these residuals by like some of our level 1 variables to see, well, you know, which one it is that's maybe causing some of that non-constant variance issue. Hotz also suggests that this test is very sensitive to the normality assumption. So if our residuals aren't normally distributed, this probably isn't a very valid test. We can get some linearity plots. Notice that these will look very similar. This is the same plot we have here again too. And we're basically just looking for any type of like curve bilinear relationship. We really want to see kind of a random scatter. We could, you could even fit like a low S line through it if you wanted to. Same thing here. We want to see, you know, sort of a linear relationship between our outcome and the residual. And here it is with our, we get a nice random scatter here, kind of randomly scattered across 0, or our predicted values that were only based on the fixed effects, 2. Here, you could check the linearity of each individual variable. And, we want to see, again, a random scatter. Maybe there's an outlier here. But if we see like a kind of a curvilinear pattern, notice it doesn't help. It's not very useful if it's a binary variable. So we'll look at, again, we're seeing some, nice evenly distributed residuals here. So it's not suggesting too much of an impact, too much of a concern. We would like this plot to maybe be rotated a little bit more, so maybe it's still suggesting that we're leaving out an important variable out of our model here, because we're still seeing some type of sort of relationship. Although if you fit like a low S line, it's still pretty flat around 0, which would indicate that it is that there isn't an issue. So I've added some syntax here that would add like the low S line to the graph. Let's see, so how now we can see it plotted in red, and it's a fairly straight line right here around 0, so it's not really indicating a problem. If we saw this line make like an S-shaped curve or like a U-shaped curve or an inverted U-shaped curve, it would indicate there'd be some problems with nonlinearity here. Same thing with our individual variables here as well. We could add in a low S line. So here we go, added in some low S. So we see the line here is still pretty flat. So it's not really indicating problems with nonlinearity. Finally, the LEM4 package doesn't have any influence diagnostics. So, if you wanted to get, like your DF betas, Cook distance, your centered leverage values, you can use this HLM dialog package, which is nice because out of all the packages we're using, HLM, SCADA, SPSS, this is the only one that actually offers diagnostics specific to multi-level models. So you can find out more information there by loading that package. Well, that is my walkthrough of multi-level modeling diagnostics in R. Please read through the diagnostics notes document I made. I gave some more pointers in there, and especially a lot more strategies for if you need to make any transformations, and then some other things about actually modeling heteroskedasticity. If that's substantively important, we can actually model it at level 1 as well too. You can't actually do it in the LEM4 package. You have to use a different one, but you can look through there and see too if you're interested. As always, if you have any questions, just let me know. Thank you.